In this first section, we'll be looking at the principles of UV and visible spectrophotometry. In UV and visible spectrophotometry, radiation with a wavelength of about 200 to 700 nanometers is passed through a solution of the compound. When a molecule absorbs energy from the UV or visible light, electrons in the molecule are promoted from their ground state to an excited state. In atoms and molecules, there are orbitals with different energy levels. Let's say the lower line represents an orbital of the lower energy level, and the line above it represents an orbital of a higher energy level. Electrons can be excited from the lower energy levels to move into a higher energy level. But in order to do this, it has to absorb energy. And this energy comes from the UV or visible light that is absorbed. If you recall the equation for energy for light, energy E equals to h nu, which is equals to hc over lambda. Lambda stands for the wavelength of the light. We can see that energy is inversely proportional to wavelength, meaning the higher the energy, the smaller the wavelength, and the smaller the energy, the higher the wavelength. So back to our energy diagram with the orbitals. If the energy gap between the orbitals is low, it means that the energy of light that is required is lower, and that means we will have a longer wavelength of light that is absorbed by the molecule. In UV and visible spectrophotometry, we are looking at the absorption of UV and visible light by compounds. However, we are also only looking at the longer wavelength UV because shorter wavelength UV, which has higher energy, is more harmful. They can break strong organic bonds. So in UV and visible spectrophotometry, we are looking at longer wavelength UV, which is more than 200 nanometers, to the visible wavelengths of light. Now let's think about the chemical structure of compounds. Different functional groups in a compound can absorb different wavelengths of electromagnetic radiation. A chromophore is a portion of the molecule's structure, so that's a functional group in the molecule that absorbs light in the near UV and visible region. So in order to be detected by UV and visible spectrophotometry, a compound must have a chromophore. Now let's look at some natural organic pigments that absorb light in the visible region. If we look at their chemical structures, you can see that a common feature of all these organic dyes are that they have a system of extensively conjugated pi electrons, meaning to say they have alternating single bonds and double bonds in their structure. Some of them could be aromatic rings, and some of them could be hydrocarbon chains with multiple alkene groups. Let's just take a look at one example, beta-carotene, which gives carrots its orange color. You can see that there are alternating double bond and single bond, double bond, single bond, double bond, single bond, and so on. Now let's look at some chromophores that absorb UV light. We can see that there are many functional groups that absorb UV light, and most of them contain double bonds. However, not all of them may actually be useful for UV analysis. If we look at the working range of standard UV spectrophotometers, they usually have a range of around 220 to 700 nanometers. So with that in mind, the chromophores that can absorb UV strongly at wavelengths of 220 nanometers and above would be more useful for UV analysis. In general, the molecules that have conjugated pi systems, which is the alternating double bonds and single bonds, would be the most useful chromophores because they will absorb light at longer wavelengths. Among the different chromophores, the benzene ring is actually the most common chromophore that's found in drug molecules.